Thank you for sticking around until the end. So my name's James Gibbard. I work at Slalom Build here in this office, so I get to sit here and enjoy this room. I've been at Slalom Build for just over 2 years now, and I'm a principal in platform engineering. And generally I spend my time working with clients building sort of cloud platforms, maybe some from scratch, some helping to improve what they have. What I wanted to talk about today is one of the more recent projects I've been working on, where we've not just been building sort of app-based cloud infrastructure, we've been trying to move computer game development into the cloud. And that's been a whole different prospect. So I thought I'd share some of the challenges that we've faced and how we are overcoming them. So we're going to spend just a few things. We're going to look at the current state of the AAA games development. So what happens generally now. And then we will go into the challenges and solutions when moving that AAA game development into the cloud, and then maybe Q&A. So a current state for games development. A AAA game, also I'll clarify what a AAA game is. It's mostly the high-profile games that have really large budgets. You can think of them like a blockbuster movie. They've got big budgets, they've got lots of global reach, they probably want it localized in lots of different languages, they want it to go onto many different platforms, Xbox, PC. But today, most of that development happens in a studio, so in a physical location with very powerful, high-spec gaming PCs that some of you probably have and play their games on. They're built on those same machines with big GPUs, lots of RAM and fast CPUs. And generally a lot of that's done in silos, so one game studio will work maybe for a publisher and then they will build and be commissioned to build the game. And that's generally how it works today. Game development can take years. It's a huge undertaking. There's lots of graphics design, there's lots of coding, there's lots of logic between the graphics and the code itself. The cost of development can be huge, and there are huge volumes of data. We're talking terabytes, potentially petabytes, but definitely terabytes of data when trying to think about from a game from inception to when it gets published. And interestingly enough, a lot of these processes, as we've been working with the games industry, I find that behind app development, there's some things that surprised me in terms of how things are done still today, and that we've had to kind of take on board and overcome. So just a bit more clarification in the type of technologies and tools that we've been working with or trying to support in the cloud. We've mostly been working with Unreal Engine, so Unreal Engine 5, Visual Studio for all of the code, C++ code essentially that gets done for the logic of the game. Games are mostly Windows built, but then can be compiled and created for Xbox and PS5s. And we're using other big graphic design tools like ZBrush or ZBrush, Blender for animations, Houdini and Maya, which are all 3D modeling tools that artists and graphic designers will interact with like they would a bit like a canvas with pens and tablets. So we're going to cover three main challenges. There's a bit of text, I'll talk about this one. Challenge one. So we've got to handle highly demanding development. So this isn't an app development, this isn't just building some of the like small Node.js or some small applications can load. We need to support creators. They need access to high-spec, low-latency, fast hardware. So we've got creators need fast PCs, they need really fast disk speeds, they need fast GPUs, they need a lot of CPU cores to be able to build and to compile the games. They need low latency access to those machines, so they need to be able to scribe and have their Wacom tablets that they're using essentially with their pens. They need to be able to feel the brushstrokes and model the graphics that they're designing. And testers need to be able to play games at a high frame rate so that they can make sure it's going to live up to what they're being asked to, the high standards that gamers expect these days. And then we also need to support peripherals and controllers, so we need to be able to allow all these developers, testers, artists to be able to plug in their Xbox and their PlayStation controllers and be able to interact with that game seamlessly and not get lag, and be able to sort of play the game as if they're testing it while they're developing. So we've been mostly working within AWS so far. The kinds of technologies we've been using to try and battle this particular challenge is some of the very large spec EC2 GPU-based machines, so G4s and the G5s. Anybody use the G5 machines? Yeah. They cost anywhere between $5 an hour to maybe $20, $30 an hour as you start to increase the size. They are not the cheapest machines. But they have powerful GPUs, and that's what we've been using to be able to deliver a desktop experience to games developers and artists. Then the other piece of technology that is nothing to do with AWS, this is quite a game industry specific technology, it's called Parsec. And it's one of the things that I didn't really have any view in. We all know what remote desktop is, and we all know how to use that. This technology is essentially doing that, but it requires a GPU. So it uses a low latency peer-to-peer network between your host current PC and the remote PC, and is using UDP traffic to essentially stream that data as fast as it can with as little latency as it can. So to be able to use it effectively, you need a GPU-based machine that you're remoting to. Parsec High Performance Relay, as it stands for. So this was something we used to be able to route the traffic, route that Parsec traffic into the regions of AWS that we wanted it to. Because by default, if you sign up for Parsec and you use it, you will bounce through their global servers. Probably somewhere in the US, but we didn't want that. We wanted to be able to put the machines into maybe into Asia or into Europe, and have that traffic going from the user as quickly and directly to the remote machine as possible. And then finally, we put that all inside the AWS VPC, helping to secure and host the compute, and essentially only make available the machines that we wanted. Hopefully some of you can see that, maybe at the back. But this is a bit of an architecture diagram that we've put together, simplified down. Within the AWS account, we've got essentially a VPC. Inside of that, we've got the GPU EC2 machines, and we have our Parsec relay sat in front of them. So the Parsec relay is in a public subnet so that it can have an open UDP port, but that's the only thing that's open. Everything else is closed so that the EC2 machines themselves are protected. And then using essentially the AWS Internet Gateway, we can route the traffic into that region. And we did a lot of testing with remote users to see how far could we stretch this solution and it still be usable. So we've managed to create like a Europe, London-based hub where we have this technology these machines deployed. And we've been able to go to places like Beijing and Brazil, and we did North Africa. And although the latency reported by Parsec was maybe anywhere up to about 200 milliseconds, the users were reporting good interaction. Maybe not the best, maybe not exactly what they may have had with their direct on their PC, but definitely something that's usable that they would be happy to spend 8 hours on and contribute to a project. So in summary for that one, we were using AWS EC2 G5s, 8 extra larges, 32 CPUs, 128 gig of RAM, and an NVIDIA GPU. Parsec provided us the redirection of audio and USB. And then, as I say, we were able to test Wacom tablets that they were using locally, plugged into their machines, that were sent over to the remote PCs. And then, yes, we used the Parsec relays to route the traffic through and made sure that we had the most optimal route to the machines that we deployed. Challenge 2, data transfer and bandwidth. Games, as I said, are huge. We're not talking about megs, gigs. So a source control repository of code could be 100 gig plus. One of the things that I mentioned about earlier in terms of that there's some things that we weren't used to in terms of app development is the games industry uses Perforce. Many people heard of Perforce? Okay. I mean, I used to use it 15 years ago, but not for a while. But the games industry uses it predominantly for everything. And that's because it deals very well with multiple different file types, including binaries, and it's able to effectively transfer things around for them, and Git struggles, some big help. So we've got huge repositories. They need fast access to shared storage and resources. So game builds, as I said, are huge. When they're compiling them, they need a lot of CPU to compile. And so there's some technology that we needed to support that helps developers share CPU time, which I'll talk about. And we also need to provide cache. So cache for the game build, so they don't have to rebuild all of the graphical assets every single time. And that cache needs to be fast. And then again, one of the more interesting things is we need to provide access to physical, real game consoles, so to Xboxes and PCs, so that you can do that compilation and even remote testing and debugging on a real Xbox or PC. And you can get, and the games industry has them, network-enabled Xboxes with 10 gigabit connections, and you can push games to them, and you can remote to them over a network connection. They have SDKs and applications already, but you can't put those in the cloud. They have to remain somewhere, either in a studio where they currently are, or maybe put them into a data center and rack them. But at the moment, AWS don't offer that as a service, or other cloud providers. So the solutions we did for that one is we used AWS EC2s, and we used something called Sony SN-DBS. Now this is the piece of technology that I was referring to when I said about sharing CPU time. This little bit of technology allows you to essentially expose your machine and its CPU as available for other people to use. And when you're doing, say, a C++ compilation in Visual Studio, you can farm off some of your DLL building to other people's computers. Now, it's an amazing technology. It can take things from hours, or let's say, I don't know, it could take your hours down to minutes, because you can distribute every DLL to, depending on how many machines you have, all over the place. But it requires a very fast, high bandwidth network. Otherwise, it's just going to be slower than doing it on a single PC. We used AWS FSx to provide the high-speed cache. So that was a technology that gives us a managed service that we can mount into the EC2 machines and provision very high amounts of IOPS. And we're able to essentially read and write really fast from essentially network storage and mount those to EC2s. And then we used AWS site-to-site VPN to allow us to connect to some physical studios where we were able to use an Xbox or PlayStation and also be able to use a Perforce server within the studio and replicate that into the cloud. And then to make it global, because one of the other requirements is to make it so that we can have this usable for users all over the world, we used AWS Transit Gateway with inter-region peering to essentially make a global network. So we were, and although it wasn't amazing, we were playing on a PlayStation in Poland via London in South Korea. So you can make it all work. It was a bit laggy, but it was okay. It worked. And again, a very small diagram, I apologize. But essentially, it's a bit more of a more detailed one. This time, we've got the same thing that I had earlier with the GPUs within the VPC, but we're using it in multiple regions and replicating, or at least interconnecting the VPCs together so that they can talk and route to each other. One thing to note in this diagram, I think, is the on-premise within for the studios and the consoles. Although the VPN worked, you're going over a studio's internet connection, say a 1 gig line, and it's not optimal. So to make, when we hopefully get to scale this, then the thing we will be trying to do is to put in direct connects where we can have maybe a 10 gigabit line, and we are able to have much faster speeds and connections between the consoles and the AWS account. So in that challenge, we basically, we used the AWS EC2s and the SNDBS for allowing studio developers to share CPU. So if you have all the developers in the cloud and they're running all of their machines in the cloud, they can then all exist on the same subnets and be able to share their CPU between them, and be able to store the Unreal build cache within AWS FSx. We used AWS VPN and Perforce for the consoles, or site-to-site VPN for the consoles, and also for accessing the Perforce repositories. We even managed to get the deployment of PlayStation games onto the consoles, and then connecting Visual Studio to a remote debugging session live to a console from essentially London to I think somewhere near Liverpool, and we were able to essentially have a live running connection between that console and the cloud machine, and to step through the code as the game was running on a remote PlayStation. And it worked surprisingly well, in fact. And then finally, AWS Transit Gateway and peering to connect it all together and try and have some centralized egress so that we can filter the internet. If we're having developers in there, we can protect some of the machines from accessing untrustworthy websites. Right, last challenge is the actual build of the game itself. Now, I've said they're big, and I've said they're hard, but I was just going to take you through the sort of general process of building an Unreal game. Because before I started doing some of this, I had never done anything within game development, so I had no idea what it took to build a game. So you have to first check out the source. That can be anywhere between 80 to 200 gig. take some time. That can take an hour, maybe, depending on the network connection. You need to compile the code and the Unreal Engine itself, because you have to build the Unreal Engine to be able to start editing the game. That can take 2 hours. This is on a single PC with a big GPU and a lot of RAM. You can then need to compile the Unreal editor code so that to actually interact with the game. That can take another hour. And then all of those data assets, the characters, the levels, the sky, the textures, everything that the artists have been creating need to be what they call cooked into an actual livable, workable game world. And that can take anywhere up to 6 hours. Then you need to package it all together, which is 10 minutes, and then you need to stage it ready for distribution to your console or your PC. That's a pretty long, drawn-out process, and currently that happens all in-house on a PC, maybe on a few PCs. So, building games is CPU intensive, really CPU intensive. And the interesting thing that I didn't realize is that I thought that the building of the graphical content would require a GPU. I just made that assumption. It doesn't. It's all CPU intensive. There are some things that a GPU, if you need them, but most of them are CPU based. Then we need it to be cost effective, even though it's at such a large scale, and we need it super fast disk speeds, because to get the best from the CPU and be able to max out CPUs, you need fast I/O. You don't want to bottleneck at the I/O before you do the CPU. And then we need to scale and distribute it on demand. So it's very linear, and it's very hard to scale it. So what do? We, again, made use of that Sony SNDBS because it's a brilliant little tool. There are other things, there are other ones called Incredibuild, I believe, that do similar things and that distribute it. And I think Unreal is actually working on their own one called Horde, which is a CI process. But this one was straightforward to use and worked. But this time I've used it with auto-scaling groups. So I've now got an auto-scaling group of machines that will start to spin up. As work gets distributed to them, it will start scaling automatically to take on more and more and more work. And then as the build starts to finish, they will start to shut down. So they're a cost-effective way, but they start to all be able to distribute that code compilation. Again, FSX for the shared storage and the cache, because it's a very fast access. And in this example, because with the group that we were working with, Team City was their preferred sort of. It was preferred. I don't know. It's still running. Okay. So Team City was their preferred CI system. So I went with that. Still good. But you could do it with any other CI system like GitHub Actions or anything. But the main thing was that Team City can interact with AWS to be able to turn machines on, shut them down, spin them up, do what you need them to do, create them from AMIs. And that helped to be able to spin up these powerful build machines that we used. And then, so one of the biggest things was the cost optimization. So to get really high IOPS, I don't know if any of you got gaming machines, but some of the gaming machines these days are using NME SSD storage with like stupid, massive read and write rates of maybe a couple of gigabits a second or more. We needed to be able to try and replicate that in the cloud. That can get expensive if you use I/O provisioned EBS volumes particularly. It can be, compared to the normal sort of standard, it can be hundreds of dollars a day to $1,000 few dollars a day. So I tried to look for a way that we could create really fast storage at a cost optimized level. And the way that I found potentially, through testing it seems to be working, is by using EBS GB3 standard drives, but using storage compute optimized machines, so particularly looking for those machines that AWS provide with that have the potential to go to high IOPS. But to get to those high IOPS, you have to have multiple disks. It won't work with one disk. So you have to have at least 5 volumes attached to the machine, and then you have to stripe those into a singular volume within Windows, and then you can start to achieve some of the read speeds that AWS say you can. And that's when we started to see some of the real performance improvements. So one of the machines we used had 128 cores and like a terabyte of RAM, and it was only able to achieve full CPU usage when we'd removed the bottleneck of I/O by using this optimized approach. Next one, and there's another small diagram for you with a bit more information about what was built for the CI system. Basic kind of server agent configuration with load balancers, the TeamCity server within containers, within Fargate, RDS database configuration, and then the build system being able to spin up very large EC2 machines within autoscaling groups. So back to our process. So what was taking 60 minutes can, with the EC2 machines and perforce caching, we can get down to 10 minutes-ish on a fast network if you move the cache closest to the machines that are wanting to check out the code. We get the 2 hours of the with SNTBS and autoscaling down to 15 minutes. We can get the Unreal Code build from an hour down to about 5 minutes. And we can get that 6 hours for graphical cooking down to about 2 hours. And that's with a really big machine. So the last two don't really change because they're pretty much optimized. So to sum up on the game building and scaling, why move? Because we can dynamically scale the game development process within the cloud. We can make it faster or slower, and we can support multiple teams within that cloud environment. We're not bound by physical limitations of a studio. We can't maybe fit more machines because they need to hire some more people, and they can't have any machines in the office. And we can globally distribute that studio. We don't have to be constrained into a single location. There are challenges as we've been through, such as demanding dev requirements, high data volumes, the ability to want to have global accessibility, and the real problem still is that access to consoles. Because if we could cloud host them, I think that would pretty much be the perfect scenario. And we used GPU-based EC2s, storage-optimized EC2s as well, GPU-based RDP, direct connect if you want to do it properly and have really fast connectivity with the consoles, and yeah, game engine automation. So really understanding that game build process and trying to split it and parallelize it where it lets you. And why wouldn't you do this? Because it costs a lot. Now, cost is a huge factor. I haven't really touched it in this, but those, as I said earlier, those EC2 machines are not cheap. If you scale this, the cost starts to get quite high, especially when you want maybe a few direct connects into different studios around the world. So the thing that needs to happen is you need to look at the project, and you need to look at the return on investment you're going to get from that and whether it's the right thing for that project. And if anybody wants to reach out, you can contact me. I'm happy to talk about any further things we find or building things in the cloud.